So this concludes the first part, and I'll continue with the second part, which is on hyperparameter tuning with mlr3 tuning. So again, there will be a first part covering, I don't know, the abstract concepts behind the package and some code examples on the PDF slides, and then we'll go through a second part of the German credit data tuning use case of the mlr3 gallery, where I will basically redo the same thing on a more concrete data set, with some more interesting outputs and results. Okay, so as most of you, I guess, will know, many of these non-parametric, non-linear machine learning algorithms that we like so much, like support vector machines, boosting neural networks, and so on, they all depend a lot, their behavior depends a lot on so-called hyperparameters, so control parameters that are not learned during the training part of the algorithm of the learner, but which are basically an input to the training procedure, and we as users have to set them, and very often we have no idea how to do that. And of course, we want to select these parameters so our algorithms work well in terms of predictive performance. Good hyperparameters are always very often data dependent, so very often good defaults are very hard to come by. And this is the reason why hyperparameter tuning, or how we often call this nowadays AutoML, or we could also call that black box optimization, has become such an important hot topic in machine learning. And what we are basically doing there is we are just trying out different configurations, different settings of the learning algorithm, and cross-validating the algorithm again and again at our data set at hand with respect to the performance metric that we're interested in, and then trying to kind of sequentially improve upon our results. And we can do this in a very unstructured manner through grid search or random search, or we can kind of do this in a more intelligent manner by using true black box optimization techniques like evolutionary algorithms, racing, or Bayesian optimization, and so on. And mlr3 tuning is there as an infrastructure package to kind of combine all of these methods and allow you to use them in any way you like, and also to connect them to mlr3. So the package is simply called mlr3 tuning. We kind of restructured this a little bit some time ago, and there's also now kind of an infrastructure package in the background, which is called BBOTK, which is for Black Box Optimization Toolkit. I'll not really explain what function is in what package. It doesn't also really matter in terms of understanding. Just load the two. I guess it doesn't really matter where the functions live in, especially for this tutorial here. So the reason why we did this is because we want to kind of reuse some of the infrastructure also in other parts. So we kind of abstracted this away a little bit. So how does tuning work like from a conceptual point of view? So first of all, we have a parameter space, and what our tuner basically does is, in a continuous loop, it suggests hyperparameter configurations, so certain settings. In this case, it might be two parameters, parameter 1 and parameter 2 here, and it's while this tuning loop goes on, we suggest a certain configuration, then we evaluate its performance by using this resampling procedure or this benchmarking procedure that Michael already demonstrated to you, and we kind of directly call into this, and all of the result objects that we're going to create here in mlr3 tuning will look exactly the same, with maybe a little bit of extra information as in Michael's mlr3 demonstration. So you don't really have to learn too many, well, at least not too many new container objects, okay? And how to access data, which I think is quite good. And that was also a lot worse in mlr2. So we evaluate the performance, which is now this blue X here. And of course, now we want to feed that back into a tuning algorithm. The tuning algorithm hopefully kind of learns something from this evaluation, and suggests a different configuration. We try this out again through cross-validation. Again, we get a performance value back, and so on and so on. And we could also even do this in batches. So some of these tuning algorithms can or want to evaluate multiple points in parallel, because that also obviously enables nice parallelization during the tuning. Think, for example, of an evolutionary algorithm, so something that's like population-based. There you could kind of evaluate the whole population in parallel. What mlr3 tuning assumes is that we always evaluate in batches. Batches can be of size 1, and then all of the evaluated performance metrics are fed back into the tuning algorithm, and the tuning algorithm iterates. And of course, at some point we have to stop. So we need also a termination criterion in mlr3 tuning. This is called a terminator, also an object that describes when you want to end. So in order for us to now evaluate performance, we need all of these objects here, which you already know from Michel's talk. So of course, there's a learning algorithm involved. Of course, there's a task involved. Of course, there's a resampling procedure involved, think cross-validation, and of course, there's usually a single metric involved that you want to optimize. And obviously, we need to extend this a little bit to define really this tuning scenario. Of course, we also need to define our search space. So what do we want to optimize over? We call this the search space, and I'll show how this is defined later on. So this would be something new. And of course, we need an object that describes when we want to terminate. Well, that's just called the terminator. That's a pretty simple thing. So we now need to tie all of this together in mlr3 tuning. So we have to create something which is called the tuning instance. That's kind of the major object. So the tuning instance is basically kind of a bundling object that takes the task, that takes the learning algorithm, takes the resampling procedure and measure the search space and the terminator object and bundles them together here in this tuning instance, or you could call this the tuning scenario, or you could also call this, I don't know, the black box function that defines how you map a certain configuration to an outcome value, a performance value, okay? And then there's also the tuner, and the tuner is an algorithm that acts on the scenario and iterates until it has produced a final configuration which is good or optimal in a certain sense. And like I said, these 4 guys here, Michel discussed already at length, so I'll now discuss these 2 guys here a little bit more, and of course these 2 guys as well. So first of all, the search space. So the search space describes what parameters we want to optimize over and in what ranges and what data types these parameters have, okay? So our basic object for this is called a parameter set that just bundles different parameters together. You have seen this already before because every learner also contains a description of what hyperparameter it has inside of it. And here we use this kind of in an alternative manner or a second time to describe our search space for tuning. And a parameter set is constructed by passing along or passing inside simply a list of parameters or parameter descriptions. So, and there's a couple of constructors for different data types. So there's a param double for doubles. There's a constructor for integer parameters, for factor variables, we'll also call them categoricals, for logicals, booleans, so to speak, and UTI, that's for untyped. That's pretty useless for tuning because tuning usually needs to know what parameter type it is and how the ranges and constraints look like. And for numerical parameters, we have usually a lower and an upper bound. So the range is what to tune inside of. So most tuning algorithms require to know this. And of course, for categorical parameters, we need to know the factor levels that we want to tune over. Well, for logicals, it's very simple. It's always true or false. So usually you don't need any extra information. And in a certain sense, you don't need this at all because you could have also done this here with the param factor. I guess that only exists for convenience and completeness sake. And if you want to see how this usually looks like, you have to load this extra mini service package here, which contains this description language for the parameters, which is called paradox. So you describe your search space here by always saying param set $new, and then you create a list and pass in description objects for all of the parameters you want to tune over with all of their respective site. So next thing, we have to define the termination condition. So we have to create a terminator object from a terminator class. I'll go over this super quickly because it's very, very simple. So we have this TRM function here, or I might pronounce this the term function, which is again syntactic sugar to create such an object. It's again a dictionary. You can list the dictionary, and here you can see all of the Terminator objects that exist. So you can, for example, say I want to stop after 50 evaluations. You can also stop with respect to clock time. So you might want to stop, I don't know, at 8 p.m. in the evening, or you might want to say I want to stop after 50 minutes of computation, or you want to stop after you have reached an accuracy of 0.95. Yeah, it's all very simple. You can just take the correct object, or you might, maybe you want to terminate when you have stagnated, when performance has not increased a lot. And it's also possible to combine all of these, combine multiple of these. Yeah, so for example, either after 1 hour or when I have stagnated with respect to performance development, and then you can use this meta terminator combo here, for example. Yeah, you can combine with and or constructions. And it's as easy as just writing term number of evaluations equals 20, and then you stop after 20 evaluations. And the next thing is you have to choose a tuning method. So for that, you need the mlr3 tuner class. That's also quite simple. It's a dictionary. Again, there's a little sugar function, which is called TNR, to create from this. And here you can list the tuning algorithms which are currently implemented. So you can do something like a grid search. You can do something like a random search. You can run a simple simulate, or actually not a simple, actually quite complicated simulated annealing algorithm here, GenSA. There's NL-opt also in there, or you can even specify exactly at what design points you want to evaluate manually. Of course, I guess some of you might be missing some more advanced algorithms in there. So we have already on GitHub a nice version of Hyperband, and we'll create very soon a new version of NLR MBO. So for model-based optimization and Bayesian optimization, currently working on that. Give us maybe 1 or 2 months so that we have a prototype that we are comfortable with publishing. And I think then you also have some pretty efficient techniques at your fingertips. So you load the tool tuner that also loads all of the underlying packages you need. Again, you might have to set some control parameters. So for example, we can create a grid search here, and we can set the resolution parameters to 3, and resolution means, so for every numerical parameter in a grid search, we discretize that to 3 values. So if I take my k from the k and n, and I want to optimize in the ranges from 1 to 20, so resolution 3 means that I'm evaluating k equals 1, k equals 10 in the middle, and k equals 20 at the upper end of the spectrum. And you can also see here some properties, so what the tuners can do, what parameter classes they can work on, the batch size settings, and so on. And of course, the strategy parameters that we have set here. But except for that, it's not very complicated. It's basically just you construct the thing, and that's it. Yeah, I know. There's usually this batch size parameter, which is important for parallelization. So I don't want to go into details here too much because that's a bit technical. And then you tie all of this together. So first of all, you create the tuning instance. So that's basically just a very long call where you pass all of these objects in here. I've explained all of this. And because I'm using grid search, and grid search always has a finite amount of points to evaluate, and usually want to search all of them exhaustively, we can also use this terminator none here. So there's not a specific termination setting. Now we just finish when the algorithm thinks it's finished. And after we have created this instance here, the scenario, so to speak, the tuning scenario, we just do tuner $optimize on the instance. Yeah? And that gives us back and also stores in the object an archive of all evaluations. And it also returns to you a data table that contains the optimal settings that were found during the tuning process. So this looks a little bit complicated, I guess, or the middle part here. So let me explain at least parts of this. So the first columns here are simply the parameters that you're optimizing over. These are always like scalar parameters because Paradox doesn't allow anything else. So these are just regular columns here in the data table, and you can just easily see them, access them, and work with them. And then here the last column is always this respective associated performance metric that is associated with this optimal configuration that we have found. here you also have two different ways of kind of specifying this optimal configuration. So I'll skip. So there's two things that can change this configuration. So later on, I will also show you how to do parameter transformations. So you can kind of transform your parameters into log scale and so on. And this stuff is stored here as a list. And you can also, maybe the learner itself has also some constant settings associated with it. So what is in this list here is what is actually being evaluated on the learner. So these are the transform parameters, also with other constant settings. Yeah? So this is kind of what is really being evaluated. And this is here what the tuner, what the optimizer is actually searching over. Okay. And if you don't understand this now, it doesn't really matter. So in most of the simple examples, all of these things here completely coincide and there's not a difference between them. And we have technical information online to make this clearer. And here I'm doing now exactly the same what I showed before. So I'm just doing this with a few more evaluations. So here I run my grid search now with a resolution of 20. Again, I create my tuning instance. I optimize over it with my grid search. I print out the results. And what you can also see is here now how I can nicely access the instance after I have run the tuning, and I can access what is called the archive slot and turn this into a data table. And the archive slot now contains every evaluation, so with every parameter setting and with every associated performance metric. And it looks exactly as this here, just a longer table with more rows, and every evaluation that the grid search has performed or that any kind of tuning algorithm would have performed is in there. And from this, because it's a data table, we can nicely now plot. So I'm here plotting this trace, or I'm plotting this K versus associated classification errors, so you can see which Ks actually work quite well and which work less well, right? So the optimal settings would be something like, I don't know, 13 or 14 for my K and N on this data set here. I mean, the experiment is more or less a toy experiment, so it's not that interesting. Here's a recap. I guess I'll skip over this because it contains nothing new. It's just the code on one page. I guess it demonstrates to you how simple tuning is. I guess what's not in here is the parameter set definition. So I guess that should be here. The instance, tuning algorithm, optimization. That's it. Okay, at least a couple of, do I have some minutes left for this? Well, maybe a few. A couple of words on parameter transformations. So sometimes we might not want to optimize over an evenly spaced range of parameters as I did before. So for example, as a motivation, so if you look at K equals 1 versus K equals 2, so the second thing here is twice as large as that one, so we might say there's a big difference between the two. But I mean, and it might be interesting to kind of evaluate both of them, but do we really care about the difference between K equals 101 versus 102? So there's a lot of parameters where you kind of want to optimize them on different scales. So other standard examples, for example, are regularization parameters where you want to try, so the C parameter in the support vector machine or the lambda parameter in regularized statistical models. Very often you want to optimize them over a range where you have values that are very close to 0 and then values that are also very, very large and very far away from 0. And then the usual trick is to optimize them on a log scale. And you can do this in a very general manner in mlr3. So you define your parameter set and then you add a so-called transformation function to the parameter set. So what does that mean? So what I'm doing here is now I'm creating kind of a fake or temporary parameter, K before trafo. Could have also called it K, I guess, it doesn't matter, just to make this more explicit. And we are optimizing this from log 1 to log 50. And now I'm creating here a transformation function which actually does X of that and then rounds it back to integer. So what this will do is will evaluate a lot of values here which are closer to 1, but it will have larger gaps between, well, larger values of K, okay? And another very regular way of defining this, for example, for the support vector machine, you might have seen this before. So if you optimize over the C parameter or a kernel width parameter, you very often optimize from something like -10 to +10, in the tuning. but in reality, what you mean is actually 2 to the minus 10 to 2 to the 10. Yeah? So 2 to the minus 10, very small values close to 0, and 2 to the 9, 2 to the 10, large values with larger gaps. Yeah? And in this case, you would write here something like param double. It goes from minus 10 to 10, and then your transformation function would just be c equals 2 to the x. Okay. And the nice thing about designing it like this is you can do any type of transformation here that you want, right? So you can kind of create fake spaces that the tuner is acting on, and then this transformation function kind of converts it into the space that you want to have the learning algorithm being run on. So I guess that's more of an expert option for people who are a bit more used with black box optimization and hyperparameter optimization. Yeah? And the nice thing is also because the trafo acts on the complete parameter set, so it's not a setting per parameter, it's kind of a function, it's an R function that acts on the complete parameter set. So this X here is a list of all parameter settings for this parameter set. You can even do multivariate transformations, right? You don't have to do it on a per parameter basis. You can act on the complete configuration and transform it into anything else. So the only thing that is kind of, required is this X here will always come from this parameter set. And what you compute here, this list, that must be acceptable by the learning algorithm. Yeah? That's kind of the contract model, so to speak, so that this will work. So in this case, what is Opera transformation doing? So you can see here how, how the tuner thinks it optimizes on this space, while in reality, we're actually evaluating here on this space, values. Yeah, I mean, that's kind of what I explained already, what this log space thing does, right? And we just call this here again, just looking at this, so there's not a big difference. We can also plot this again, so there's also nothing new in here. So I'm now plotting this k before transformation, which I guess is a little bit, I don't know, the scale might be a bit confusing for people because it's now this numerical scale or this double scale, which goes from 0 to 4. But in reality, we are actually optimizing from 0 to 50. And this is also why this, let me show this again, why this X domain here is interesting, right? Because this here contains what the tuner is acting on, this before the transformation, and this guy here contains the configurations after the transformations, which I guess are more interesting to people to later analyze. And I've shown here both. If you dislike that these parameters here are kind of, hidden down in a list, this archive thing here and many of our data tables that we are supplying with mlr3 have these unnest functions or unnest options. We can kind of unnest everything from the list, and then it will create separate scalar columns in the data tables. You can easily access them, which is pretty convenient. So finally, I guess no hyperparameter tuning talk is complete without referring also to nested resampling. So I don't want to go into theory here so much. So I'm assuming that most of you know that we need to perform nested cross-validation or train validation test setups to estimate learning algorithm performance in an unbiased manner if we do hyperparameter tuning. Otherwise, if we only kind of, if you optimize on the cross-validation for performance estimation, this will create optimistically biased results, and we shouldn't do this. So in order for us to achieve simple nested resampling through mlr3, what we are doing here is we are actually creating something that's called an Autotuner object. And what the Autotuner object does is it basically creates a two-step procedure. So as a second step, it really runs your learning algorithm with the optimal configuration. And the first step here is this tuning thing. So basically does what I've just shown to you. It runs the tuning completely first until completion. It computes the optimal configuration here, and then it finally trains the model on the passed in data set with this optimal configuration. And then we just kind of, in a software engineering manner, tie a box around this, and we create a coupling mechanism that runs the tuning first and then the learning algorithm, and this is what is called the Autotuner. And the nice thing is, if you cross-validate this thing here, yeah, this has now an outer cross-validation and an inner cross-validation in the tuning, and this kind of automatically does everything correctly because you cannot cheat anymore, because in the outer loop, yeah, always fresh test data is being used. If you find this confusing and you don't know nested resampling, really pick up, I guess, a good book on machine learning evaluation. I've also, I guess, published papers on this. Really look this up because it's pretty important for practical work and proper evaluation. So many people have done mistakes here. Nice thing about mlr3 in terms of software is it's super simple. You can now just do the following. You create an autotuner, which takes your learning algorithm. You can even pass in some constant settings here. You create an inner resampling, or pass in an inner resampling. So this is what is being used during hyperparameter tuning. Here you specify the metric that you want to tune over. You specify your search space. You specify your termination criterion, and you specify your tuning algorithm. And all of this stuff here you have seen before. So from here to here, this basically defined the tuning instance. Well, I guess this also needed the task. We can't pass this in here because this will create an abstract learning thing that can be trained on anything. And this here was the tuner. But all of these objects you have seen before, we just now tie them all together in the autotuner. And what you can now do is this autotuner is simply an mlr3 learning algorithm. Yeah? It behaves, it's completely connected to what Michael has shown to you. So you can run every method that Michael has taught you on this thing. For example, you can train it. And if you train this, this will run this very complex process here. It will run the tuning first, compute the optimal configuration, and then fit the model on the task with the optimal configuration. And this is what I'm doing here. You can even now see the optimal settings that were computed by this, if you access this here. You can also do this somewhat lengthy call. So I guess we should probably create an active binding for this. You can access in this, you can access the complete archive again. So everything that basically led to this optimal configuration while tuning was being run in the autotuner. Or you can resample the thing. So you can resample your autotuner here on Iris with an outer resampling now, store everything that's being computed, and that now really computes nested resampling. It gives you access to all of the optimal configurations. It gives you access to all of the optimal, all of the archives of all outer loops and so on. Again, some of these calls might be a bit lengthy in the beginning or hard to remember. This is all covered on the cheat sheets. So I guess take a look at the book to understand the underlying principles, or rewatch what I did here. And then later on, if you just want to remember how you have to kind of, how the API looks like, have a quick look at the mlr3 tuning cheat. It's one page, it's all in there. And that, I guess the last parts of the sheet really explain again how you can access all of these results. What is being computed here now by this resample function, the performance metrics, these are guaranteed to be unbiased and proper. So, okay, so what did I do? So this is here the second post. So this is mlr3 tuning on the German credit data. So Michael, I think, already explained the first part very well, right? So how to kind of benchmark algorithms on the credit data set. So now, of course, we could also use the benchmark function to try out different algorithms, to try out different configurations, to see which of these works a bit better. And optimize on this, but A, this is inconvenient, right? And B, at some point it would become cheating because you'd be optimizing on the cross-validation. So I'll just go through the motions again to show you how to do this with mlr3 tuning. Before I do this, let me just set some chunk options just for layouting, load some stuff and set some seeds. So the first thing that's maybe interesting to you is this here. So every package in the mlr3 universe is kind of operated by the same logging mechanism. So we use this logger, LGR logger package, and you can just always say get logger package name, and then you can set the threshold. So you can, for example, because I will now be calling into quite a few packages, right? Especially I will be calling into Michael's mlr3 package, and so internally I'll use the resample and benchmark function. That creates a lot of logging output, right? Which is nice if you just do normal benchmarking, but which becomes super annoying if you do lengthy tuning runs. I'll set this here to warn, so I don't want to see this. But for black box optimization, I'll set the threshold to info, so I do see which configurations are evaluated. And actually in the gallery post, I think this is also set to warn to reduce output and length a bit, but here, I guess for the live tutorial, I'll set this to info. So I'll just, again, skip through the text. So first, we'll just load a couple of packages. So that's not very interesting. You already know this. So of course, we load mlr3. We load a bunch of different recommended learning algorithms. We load the tuning package, and we load paradox, so we can talk about parameter spaces. Again, let's also set the theme for ggplot. And now we'll start. So first of all, let's just get our hands on the example task of German credit. So I'll just load this into the session. I will not enable parallelization here on my laptop, but if you have a faster machine with more cores and just want to run the thing faster, just enable future here with plan multiprocess. So before I start with tuning, I have to, of course, now specify how I want to evaluate configurations through resampling. And German credit data task is of medium size. So very often our standard here is to use 10-fold cross-validation. So I'll do that. I will also instantiate that. So I'll really create all of the splits. So later on, because I'll try out different algorithms and different configurations, so I really make sure that I will all evaluate them on the same splits to reduce variance in comparison. So most of our functions like benchmark and tuning and so on, I kind of do this internally. So you don't, if you forget this, I would say in most cases, yeah, we don't have to worry about this, but here just to make sure, especially when I want to compare different algorithms, I just want to make sure that this is instantiated and we're always using the same splits for every comparison. And I can even take a look at this. So if I wanted to, I can see now in the instance, I can see the row IDs. So I can see here, for example, the first fold. So which row IDs or which observations are in the first fold. And I guess if I click here a bit more, you can see, okay, that's the 10th fold, and in between are the other guys. And as before, I will now use a k-nearest neighbor method as my classifier for German credit. I will use the k-knn package. That's a nice flexible implementation of the k-nearest neighbor algorithm. And I'll set predict type to prop to predict always probabilities and not only hard class labels. And here you can also see how I'm setting now a specific constant hyperparameter that I'm not tuning in the beginning, at least. Set the kernel of the knn method to rectangular. So as a next step, we have to now decide which hyperparameters we want to tune. And if you don't want to read the documentation of kknn, you can also ask mlr3. Michael showed this already too, which parameters exist in knn, or in kknn, I should probably say. So you see the k parameter, the number of nearest neighbors. You can see a setting for the distance function, so which norm to use, so L1 norm or L2 norm, so Manhattan distance or Euclidean distance or something numerical in between. That's a double parameter. You can see this kernel here. That's the kernel function that basically weighs the example in the distance computation, and whether you want to scale features before you use knn. And usually, I guess, if you know knn from a more algorithm or theoretically minded course, you know that it's a pretty good idea to scale features before we use knn, and you will also see this later on in our empirical results. So of course, now I have to specify my search space, and I want to keep it simple in the beginning. So I'll only tune over k. So I go from here from 3 to 20 in this example, and I will also tune over the distance parameter, but I will only do this in an as an integer parameter. I could have also used the double here because we can use kind of an L distance type of metric, where this distance is a real value. But here, to keep it simple, I want to try out the values of exactly 1, 2 as integers. So let me define this with this 2. And now I'll go through this quickly. I create the instance as before. I think I mentioned this now 5 times. Pass in the task, pass in the learning algorithm, pass in the resampling, specify your measure. So we'll use here classification error to optimize, pass in the search space. And because later on I will use grid search in the beginning, I'll just set the Terminator to none. So, okay, let's execute this too. And we have seen before how to set up grid search. So we use TNR of grid search. I set the resolution to 18 and I set batch size to 36. So that might be interesting. So first of all, what does resolution 18 mean? So what this means is that we are using, for this guy here, we're actually using 18 different values. For this, we can't. We can only use 2, right? It's because it's an integer parameter that only goes from 1 to 2. So this means in the cross product of this space, there's 18 times 2 different configurations. So there's 36. And because grid search is embarrassingly parallel, right? There's no interplay between the different evaluations we set. Because it's such a, I don't know, stupid, simple algorithm, I now set batch size to 36, which means if I would enable parallelization, everything would be evaluated in parallel, okay? Because nothing is sequential, nothing depends on each other. So this would kind of enable maximal parallelization, yeah, so to speak. And on my laptop here, it doesn't matter because I'm just using 1 core because it's kind of a small and small laptop. Okay. And I can now take a look at this instance here and have a look at the results slot. And what I get back from that is something super uninteresting. It's just null because I haven't run the tuning yet. Okay, so it's just empty. So we can now use run the tuner with the optimize function on the tuning scenario. And if we do that, you can now also see here that it's starting to tune and running and evaluating 36 configurations. Yeah, we just have to wait a little bit, I guess 1 or 2 minutes, to see how the result looks like. It's finished. So I guess I could explain also the logging a little bit. Here you see timestamps. You can see this logging level, so this info, right? You can see here we are optimizing 2 parameters. You can see we also print out which optimizer we use, the Terminator. You can see that we have to wait for 36 evaluations. And here we can now peek into the results. So I guess you can see this here. Okay, something is wrong with my, I don't know, I guess I messed up something in my R session at the moment, so this shouldn't happen, so it should be printed out. So this is how this looks like. You can see that I now chose k equals 9, so 9 nearest neighbors, and I'm using Euclidean distance. And this is the optimal classification error that I obtained with this configuration, which is 25% of misclassifications. And as I said, this is already a bit biased, okay? Yeah, so this is not an unbiased estimator for future performance on new data. Sorry. I also already showed to you how you can access the archive. So you peek into the instance, you access the archive, and then you convert it into a data table with $data. And you can see here the unnested parameters that we're optimizing over, so k and distance. So this is our grid. So if you're wondering why the parameters are actually ordered maybe a little bit weirdly, so we also randomize the order of the grid search for some technical reasons. And here you see the classification error in this column, so all pretty equal. And again, we can plot performance. And here I'm not only plotting k on the x-axis, I'm also coloring the distance parameter, so you can see whether that makes a difference, right? And on the y-axis, I obviously have the classification error. So you can see here that on average, Euclidean distance works, well, a little bit better, a tiny bit better. Okay, so let's make things a little bit more interesting. So how about we now want to search over a larger parameter space? So I now want to optimize over k from 3 to 50. And I also want to do this on log scale, as I explained before. I now also want to truly optimize distance. So this parameter of the distance metric as a true double, and I'm going from 1 to 3 as a real number. I'm also now optimizing over the categorical parameter distance kernel, and I'm optimizing over rectangular, Gaussian, rank, and optimal. And I will also optimize over the Boolean parameter, the logical parameter, whether to scale features or not. So let me define this. So this is now 4 parameters, a bit more kind of challenging as a search space. And I will also do this log space transformation that I did before as in the slides. 4K. And because this parameter space is now a bit larger, so maybe you don't want to do grid search anymore, right? Because grid search would now exhaustively evaluate everything. This might get quite expensive. So the next best algorithm, if we don't want to do anything too advanced, would be random search, where we can completely control how many evaluations we want to do, because it's just randomly samples our search space, also embarrassingly parallel. And then I really have now to set a termination criterion. So I set this again to 36 evaluations as before for the smaller search space, and I set batch size to 36 again, so that this is completely parallelized. So let me execute this again. And yeah, I guess I will skip over this now a little bit because I'm not patient enough to wait again for 2 minutes. So this again now, and I did this before in my dry run to prepare the tutorials. You can see here how the result looks like. So this has optimized now these 4 parameters here. You can see the optimal configuration here. You can see that the classification error is now a little bit better. Obviously, we should have probably used the larger budget, I guess, for 4 parameters and not only 36. And you can see the complete archive here spanning, again, these 4 columns and all evaluations. And as you can see, we're also storing all of the resampling results, all of the predictions, all of the evaluations. You can configure this a bit. If you think this wastes memory, you can switch this off. But if you want to peek into all of the computed results, that's definitely possible. And it's just in there. Michael has taught you how you work with these objects, and you just have to access the data table and get it out of this. And here again, I'm now unnesting for the transformation. So if you're annoyed by this K being on log scale, you can unnest here and you can see it on the original scale. I guess we would have to round this also. No, actually, I'm being stupid. I'm being an idiot. So if we are unnesting the X domain, I have to click here. Just you can see here the unnest, the transformed K on the original scale, and of course, there's also an integer. Sorry. I misspoke there. And you can now do nice things again. You can plot with ggplot on the archive. So here I'm, I should have done this, sorry. Okay, I'll skip that. So I guess because I should have computed the other thing before. So this, actually, let me just kind of directly skip to the most interesting part. So here, so I've shown the Autotuner again, so there's not a lot of new stuff in there. So I think the most interesting stuff in terms of the use case here is in the appendix. So in the appendix, we are running the same thing. So I'm running exactly the same task with exactly the same search space and so on, but I'm doing more evaluations. So I'm actually doing 3,600 evaluations. So we are increasing the budget by a factor of 100. And because you don't have to pre-compute this, we have actually stored all of the results here in an RDS file. So we pre-computed this a bit. I'm not sure how long this takes, maybe about an hour or so. Again, structurally, the results look exactly the same. It's just now 3,600 rows. But you can now see very nice effects from this if you just use ggplot on the archive. So here you can, for example, see K versus classification error, but we colorize points by whether to scale or not. And as you can see, obviously scaling is beneficial and helps, right? And this is what we teach to you, what I teach my students, for example, if I teach KNN in a university lecture, I teach them to, because it's based on this distance, Euclidean distance function, usually it's a good idea to kind of become, well, scale independent if features are measured in different units to scale everything before, right? And here you can kind of empirically see this, right? Results are much better if we scale. So of course, you could argue, well, I know this already, so why should I tune over this? You can shortcut there if you know that. In some other cases, it's less clear, and it's at least see these toy examples, it's kind of nice to see this again, right? I can also colorize points by kernel. And here the picture is a little bit less clear, right? So there seems to be some patterns in there. So in order to kind of make this a bit more visible, we are now also using geom smooth. So this is my kind of more now talking about ggplot and mlr3 tuning. You can see here these smoothed lines, these average lines. I guess you can see that, I guess what you can at least see if we zoom in is that there's apparently also, well, there's a certain dependence going on between K and the kernel, right? So depending on what kernel you use, different values of K are optimal. And there's also, well, at least a rough dependence also between distance and kernel. So from these very simple plots, we can now already get a lot of information out of that. So scaling seems to be very influential. Setting scaling to true is beneficial. The distance parameter actually seems to be the least influential. And there seems to be an interaction between K and kernel, and also, well, yeah, to a certain extent, not that much actually between distance and kernel. The only part that I skipped here is how to do proper auto-tuning, proper nested resampling. But the only reason I skipped that is because it looks exactly the same as on the slides.